In this video, we'll take a look at two circumstances in which Newton's laws fail, in which you cannot apply the basic concepts of Newtonian physics. Start off by understanding motion is relative. The idea of relativity, general relativity to be exact. It's an idea that's been around since Galileo was trying to convince the masses that the Earth revolved around the sun and not the other way around. When you look at the Earth around you, it feels like the Earth is not moving. When we see things move across the sky, it's easier for us to say that those objects must be moving while we stand still, as opposed to the other way around. And the idea is pretty simple. The way that the motion of an object is described depends entirely on the frame of reference by which it is observed. Let's look at an example of an alien dropping a thermodetonator in the back of a truck. So this alien is standing in the back of an 18-wheeler inside the trailer part, holding his little thermodetonator, and he drops it. As the alien watches the thermodetonator fall, it travels in a straight path to the ground, landing directly beneath where he drops it. From the alien's perspective, the thermodetonator drops straight to the ground. This would be the case even if the truck were moving at a constant velocity of 50 kilometers or miles per hour. If this alien is in the back of this truck, and if this truck is traveling forward at a rate of 50 kilometers per hour, as he drops the thermodetonator, he's still going to see the exact same thing. The thermodetonator is going to drop straight to the ground. That's the way he perceives it because of his frame of reference. The frame of reference in both scenarios is the truck the alien is standing in. When the truck is stationary, its position relative to the alien remains the same. When the truck is moving at a constant speed and the alien is standing in the back in the trailer, still, the position of that truck to the alien stays the same. We have the same frame of reference, so we have the same description of motion. And again, it doesn't matter if this truck is totally stationary. This back axle is a certain distance away from the alien, and it stays a certain distance away from the alien, thus the perception that the truck is not moving. The tractor part of the truck is a certain distance from the alien, and it stays that same distance from the alien, thus the perception the truck is not moving. Even at a constant 50 kilometers per hour, this back axle is still the same distance away from the alien, and it still stays the same distance from the alien. The cab, the tractor part of the truck, same distance from the alien, and it stays the same distance from the alien. So again, there's this perception to the person standing inside that trailer that nothing's moving. And as long as they're perceiving no motion, that thermodetonator drops straight to the ground. Now, how do we change that? We have to change the frame of reference. We have to change how we're looking at the scenario. Add a second alien standing outside the truck. To the second observer, there's more motion taking place because this motion that the truck has will change its position relative to the outside alien. Again, to the alien on the inside, this back axle is always the same distance away from the alien. But as this truck moves, as the truck would move, this axle will be getting closer to this alien on the outside. To the alien on the inside, the cab or tractor part of the truck is the same distance away from the one inside, and it stays the same distance away from the one inside. But to the observer on the outside, it's going to be getting further away as time passes. So the frame of reference suddenly changes. And because of that, while the observer on the inside sees the thermodetonator fall straight to the ground, the observer on the outside would see the thermodetonator follow a curved path to the ground. Because there's two parts of motion happening. There would be the vertical part of the motion that pulls the thermodetonator down because of gravity, plus a 50 kilometer per hour forward motion that the truck gives it. there would be two components of motion there, and anytime you have two components of motion, you would get curved motion, projectile motion. So the outside observer, it would appear something completely different. And that is because the frame of reference has changed. The frame of reference for the person on the outside is the earth, the ground that they stand on. The ground that they stand on is not moving. So this little part of the ground here stays the same distance away from the observer on the outside as this little piece of ground over here does. The ground is the thing that's not moving. The frame of reference is entirely different. It's the earth this time. The position of the truck to the outside observer is changing, and it's that additional component of motion that causes their description of the way the thermodetonator falls to change. There are two components of motion for them, for the person on the outside. There's the vertical component produced by gravity and the horizontal component produced by the truck, combining together to give that ball a curved path. This is what we mean when we say motion is relative. This is the founding ideas behind the theory of relativity. What each situation has in different is a different inertial frame of reference. The inertial frame of reference is some perceived stationary object. It's either something that's truly stationary or something that's moving at a constant velocity, but is perceived as being stationary. It's assumed to be stationary, and the motion of that object is judged against that inertial frame of reference. For the alien that's inside the truck, the inertial frame of reference is always the truck, because that's what they perceive as not moving. That's the thing that surrounds them that stays in the same position. As long as that truck doesn't accelerate, speed up, slow down, or turn, it'll act like it's standing still, and it will be an inertial frame of reference. For the outside observer, the inertial frame of reference is the earth. That's the thing that is perceived as not moving, even though it definitely is moving. It's moving 1,000 miles per hour around its axis, and it's hurtling through space at 67,000 miles per hour. The Earth definitely moves, and it moves quite a bit. But our perception of it, the way we see it, is as a stationary object. And that's what makes it our inertial frame of reference for so many situations. Now, why is this inertial frame of reference so important? Newton's laws only work if you have one. Newton's laws require an inertial frame of reference for them to be applied. So when we talk about Newton's laws and where Newton's laws apply, they apply in conditions where you have an inertial frame of reference. There is a perceived stationary object that the motion can be related to. If you have no inertial frame of reference, then there's no Newton's laws. There are other instances in which Newton's laws don't apply. The microscopic world of subatomic particles is another place where you can throw Newton's laws out the windows. We're talking about the world of atoms, molecules, protons, neutrons, and electrons. They don't follow Newtonian physics. They follow something called quantum physics. And the world of quantum physics is an entirely foreign one. There's an entirely strange one that has nothing to do with the world that we live in, the macroscopic world with inertial frames of references. In the quantum world, the subatomic world, the world of protons, neutrons, electrons, atoms, and molecules, objects follow the uncertainty principle. The uncertainty principle states you cannot simultaneously know the position and the momentum of these particles. You can't know where they're at and where they're going at the same time. This is very different from the macroscopic world we live in. When I see a car going down the street, I can calculate its momentum, and I can make a prediction about where it's going to be a second from now. And that prediction is going to be pretty accurate. In the subatomic world, you can't do that. You either know where it's at, and you have no idea where it's going, or you know where it's going and you have no idea where it's at. That's the Heisenberg uncertainty principle, and it may sound familiar to you because it does come up in chemistry classes. It's one of the reasons why the old planetary model of the atom had to be discarded and the new electron cloud model or quantum mechanical model had to be developed. Objects can also be in two places at the same time in the quantum world. You can fire an electron at two slits in a piece of metal, and the electron will move through both slits at the same time, literally being in two places simultaneously. Again, that doesn't happen in our everyday world. In the quantum world, nothing is linear. There is no such thing as a linear increase or decrease. Everything happens in steps, jumping from one step to another, not smoothly moving from one step to another. For example, when we climb stairs, we fluidly move from one step to the next. Our body will be in positions between steps from time to time as we literally move up the stairs. Electrons move through energy levels very differently. They don't climb those levels, they simply disappear from one level and reappear in another level, never existing in between. Again, that's the quantum world. Imagine riding an elevator and the floors of the building being the levels of the building. You can be between floors. As the elevator rises up, you can be between the third floor and the fourth floor. An electron cannot be between the third level and the fourth energy level. It's either in the third level or it's in the fourth. There is no in between. And to get from the third to the fourth, it has to absorb a quanta of energy. And as soon as it absorbs a quanta of energy, it'll just disappear from the third level and just reappear in the fourth one. No perceived motion between the two. To get back down to the third level again, it would have to release that quanta of energy. And again, if this all sounds very familiar to you, that's because you took chemistry. And this is the whole premises behind the Bohr model and how we moved from the planetary model towards the modern one. Getting rid of this, the electron can be anywhere idea to they have to exist within certain energy levels around the atom based on how much energy they have. There is no continuous there. It's just a bunch of steps. We believe the real world works in the same way. For example, when you accelerate a car, it accelerates in steps. The car will absorb a quanta of energy and jump to the next step and speed up a little bit instantly. No continuous linear about it. It just jumps from one speed to the next. And then it'll absorb another quanta of energy and it'll jump to the next level, again, jumping instantaneously from one speed to the next. It's just in this real world, we're so big that we don't notice the steps. The steps look and feel smooth to us. If you're a gamer, you understand this all too well. Old games back in the days of cheap, well, they weren't cheap, but poor performing graphics cards, curves always looked like a bunch of straight lines connected together. And you could see little steps in the lines. Well, that's what it looks like on the quantum world. You can see the steps. The modern world is like the modern graphics card where the surfaces look perfectly smooth. And the only reason why the surfaces look perfectly smooth is because the little steps are so small. You can't see the steps anymore. That's the quantum world. That's the quantum physics world. Newton's laws apply in our world because the steps are so small and we can practically ignore them. But if you get down to the quantum world, the world of atoms and molecules and protons, neutrons, and electrons, then Newton's laws just don't apply anymore. Newton's laws also don't apply to objects that are moving near the speed of light. This is called special relativity. There are some very strange things that happen to objects as they approach the speed of light. Equally strange is the quantum world, if not even more strange than the quantum world. One thing that happens as objects approach the speed of light is that time slows down. This is called time dilation. You've probably heard before, if you take a 20-year-old person and put them on a spaceship, send them out at the speed of light for what they feel like is a year of time, they'll come back to Earth being 1 year older. But then everybody else on Earth will be 40 years older. That's due to time dilation. As you approach the speed of light, time slows down for you. Now, because of relativity, you don't notice. It feels perfectly normal. It feels like a year to you. But to the outside observer watching you, it's more like 40 years that goes by. And you could return back to Earth and find everybody that you left behind has passed away from just old age because you've been gone so long. And you wouldn't notice it because time slows down. It even happens at the speeds that humans approach. Our GPS satellites that are in orbit have to be programmed with time dilation in mind. They are geosynchronous satellites. That means they stay in the same position over the Earth all the time. That means they have to move as fast as the Earth does. So they're moving over 1,000 miles per hour. Because of that, time is slightly different for them than it is for an object on Earth that isn't moving. So the clocks on the GPS satellites have to be adjusted to take into account for that. And it's only milliseconds that it would change per day. Only a very few number of milliseconds per day would be lost by the satellites as they're in motion. But because of the distances they are away from Earth, that would put the GPS signals off 7 miles every day if the satellites didn't adjust for how fast the satellites were moving. The lengths of objects also change as they approach the speed of light. The literal size of an object decreases as it approaches the speed of time, or speed of light. This is due to the decrease in time again. Speed of light is a constant. And as objects are approaching the speed of light, time is going to slow down. But the speed of light is still a constant. So that means that the length of the object has to decrease or dilate at the same time to maintain the same ratio, keeping the speed of light 300 million kilometers per second, or meters per second. So how do you fit an 80-foot beam of wood into a 100-foot barn? Get it moving near the speed of light. As it approaches the speed of light, the beam will actually shrink in size to the outside observer, to the point where it would be, that should be the word, where it would be shorter than the barn. I should say a 100-foot beam in an 80-foot barn. Yeah, it's pretty easy to put an 80-foot beam in a 100-foot barn, just put it there. But you can put a 100-foot beam in an 80-foot barn by getting it to approach the speed of light. That, again, that dilation of time that happens as the object approaches the speed of light causes a dilation in length in order to keep speed of light a constant. So you can put a 100-foot beam in an 80-foot barn by speeding it up and making it approach the speed of light. Again, this happens to all objects on Earth. Time dilates for us when we're traveling in an airplane. Length dilates for us when we are traveling in an airplane going 500 miles an hour. It's just that the dilation is so small we don't notice it. The mass of an object also changes as it approaches the speed of light. Again, it's in order to keep the speed of light constant. As an object approaches the speed of light, its mass will increase, approaching infinity. Technically, the mass of an object at the speed of light would be infinite. Because of this, it would take an infinite amount of energy to get an object to move the speed of light, which is why most physicists would tell you it would be impossible to get a human spaceship to move the speed of light. It would take all the energy in the universe focused on that object at the same instant in order to even get it close. You would have to have an infinite amount of energy to get an object with mass going the speed of light. Now, photons can do it, the particles, the pseudo-particles that make up light, because they have no mass. Because they have no mass, they're not affected by this phenomena. But a regular object would be. And as a result, Newton's laws will not apply. In those two crazy extremes, the world of atom and molecules, the world that's governed by quantum mechanics and quantum physics, and objects approaching the speed of light, those objects that are governed by special relativity, Newton's laws don't apply. Again, you can throw them out the window. Physicists are working on a way to bridge the gap between these worlds, looking for what they call the theory of everything, a single set of equations that would unify all conditions and would work under all conditions. That's one of the holy grails, if you will, of physics.